In this question, okay, masses of 4 kilograms and 6 kilograms are suspended from the ends of a light, inextensible string which passes over a pulley. The axis of rotation of the pulley is horizontal, perpendicular to the pulley, and passes through the center of the pulley. The moment of inertia of the pulley is 0.08 kilograms per meter squared, and its radius is 20 centimeters. The particle, instantly know here, guys, this is in meters, this one is in centimeters. Immediately convert to meters. The particles are released from rest and move vertically. When each mass has acquired a speed of 1 meters per second, find the common acceleration of the masses and the tensions in the vertical portions. Tensions. It hints that it's two different tensions. Let's call it T1 and T2. Now let's explain the difference between this section and a smooth pulley. A smooth pulley is what you have in particle dynamics, or connected particles. A smooth pulley doesn't actually rotate. The wire actually slips across the surface. Okay? It's like a string falling off the edge of a table if it's connected by heavy objects. It's actually sliding as opposed to causing the wheel to rotate. When the wheel rotates, or when the pulley rotates, as it does in this section of the course, the tensions in both of them are different. Plus, it also gives you a hint in the question, tensions. Okay? So please remember this. When the wheel is free to rotate, tensions are not the same. Got it? Okay, let's begin. What we're going to do first and foremost, just going to write down 4G, 6G. We also know that 6G is going to be accelerating. The acceleration is still common because they're connected. Okay? The wheel is going to be rotating this way. Okay? Now, let's write down a formula that sorts all this out. I is 0.08. Now, let's figure this out. Part 1. Gain in kinetic energy. Gain in KE equals loss in PE, potential energy. Okay? Now, the loss in potential energy is actually complicated. Can anybody tell me why? The 6G is losing potential energy, but the 4G is gaining potential energy. Do you understand? So when the 6G drops down 6GH, yeah, the 4G goes up 4GH. Its potential energy goes up 4, because remember, it's mass times, it's weight times height above the ground. So look at this. Loss in potential energy is going to be 6GH, the weight multiplied by the loss in height, but we're going to have to take away 4GH because the 4 kilogram particle actually gains potential energy, 4GH. So the loss in potential energy is going to be 2GH. Is everybody with me there? One of them goes up, the other one goes down. One of them gains energy, the other one loses potential energy. Now, next thing we've got to do is gain in kinetic energy. Okay? Gain in kinetic energy. The kinetic energy occurs in two ways. It occurs with the rotational energy of the wheel, which is a half IW squared. It's going to be a half mv squared, the movement of the 4 kilogram particle, and there's also going to be the movement of the 6 kilogram particle. So there's two kinetic energies and one rotational energy. Okay? Now bear this in mind. So there's our loss in potential energy in red to the right, and what we're going to have in we've got purple to the left is our gain in overall kinetic energy. We're going to have a half the inertia, which is 0.08 W squared, which is going to be 5 squared, plus a half 4 times v squared, which is going to be a half 4 times 1 squared. How do we know it is 1? The question says when each mass has an acquired speed of 1. So it means we're talking about when they're both moving at a speed of 1. Okay? So a half for 1 squared plus a half 6 times 1 squared. Okay? We can add these all together just using the calculator, all in one swoop, and what we're going to find is it's 6. 6 equals 2GH. Okay?
Where did you tell me to be found?
Sorry, W. Let me find out. Oh, where to get W equal to 5? That's a good question. Okay, just let me look at the information.
Well, you can work it out.
Sorry, I think it's this, okay? Phi equals RW. Okay? And phi is going 1 meters per second because the rotation has to be going 1 meter per second, so 1 equals RW. So, sorry, 1 equals 0.2 W. So number 1, sorry, that looks like an I. 1 equals 0.2 W. Divide 0.2 into 1, W equals 5. So look, it's doing 5 radians per second to keep up a speed of 1 meter per second, okay? On the outside. So then what's going to happen? So that's where our 5 comes from. Good question. Okay? Next thing is H equals 3 over G. Is that alright? H equals 3 over G. Now, next part. Common acceleration. We still have to find out acceleration. We're going to use v squared equals u squared plus 2as, or, technically speaking, 2a h. How far we dropped. Now, velocity squared equals 0 plus 2 times the acceleration times the drop, which is 3 over g. Okay, what do we know about v, guys? The final acceleration is 1. 1 squared equals 6a over g. A therefore is going to be g over 6 ms to the minus 2. Okay, and now finally part 2, the tensions in the vertical portions of the string. Write down both equations. Okay, for the 4 kilogram particle, which one's winning, tension or weight? Is it going up or down? Tension's winning if it's going up. So it's going to be tension minus 4g equals 4a. For the 6 kilogram particle, 6g is winning, the weight's winning, the tension's trying to hold it up, but overall it's going down. Okay, put in your value for a. So if I put in a here, which is g over 6, what's going to turn out to be is 2g over 3 equals t minus 4g. Bring the 4g over the other side and add it. 2g over 3 plus 4g. And what we get is 14g over 3. Is that T1 or T2? T1. And then for T2, T2 is going to be 6g minus 6a, which is going to be T2 equals 6g minus 6 times, what's it, g over 6. And this in turn gives me T2 equals 5g. And that there is a full question.